Guys, my name is Ramdas Satyan. I work for AMD in the algorithm team, where we design high-quality hardware encoders for the data center. Today, I'm excited to talk about applying AI/ML techniques to improve compression and video quality for live video transcoding. So, I'll start by introducing real-time transcoding and what are the requirements we need to do it at scale, and showcase AMD's Alveo MA35D transcode card, which is meant for the data center and its capabilities for live transcoding. And we're going to switch gears and talk about the AI/ML techniques which are being considered at various stages in the pipeline of the transcoding use case. And then the bulk of the time is going to be on two tools, the region of interest and content-aware encoding, which we have productized in the MA35D transcode card. And finally, some results on that. So live streaming, right? I mean, we don't need to mention too much about this, right? It's reshaping the way we engage, communicate, and entertain with the world, right? So people who are seeking real-time experiences and interactions are hugely using live streaming. And platforms like Twitch, YouTube Live, Facebook Live, and others have become go-to destinations. So in a 2021 survey, they saw that the global streaming market live almost constitutes around 70%, and it is growing rapidly. So to do live streaming, right, real-time transcoding plays a crucial role. So, to deliver high-quality, compatible, and optimized video content to these audiences who are using a wide range of devices on different platforms, and they have different bandwidth constraints. And this is typical of a transcoder, right? You have a decoder, a scaler, and an encoder. Now, what are the requirements to do it at scale, right? So traditionally, right, in a traditional broadcast scenario, right, there were few ingest streams and sending to millions of people, right? Now, everyone wants to be a streamer, everybody is contributing and consuming, right? So you've got many ingress and egress streams, right? And then with new people coming to stream, right, you've got a huge tail, a long tail of a lot of videos being recorded, and it might not be viewed by many, but at least the generation of these videos is at a massive scale, right? So all of these video streaming platforms, right? I mean, if you look at the amount of videos they are generating, it's close to many petabytes a day, right? So this suggests that the compute is increasing exponentially, and we want to support newer generation standards like AV1, AV2, VVC, right? And we want to cater towards higher resolutions, 4K, 8K, right? And AR and VR is also becoming very popular. And with gamers, right, we want frame rates of greater than 60 FPS, right? So 120 FPS if possible. And also what we are also seeing is that these interactive media applications, right? So people want interactivity, right? So there's a huge requirement for very low latencies. So keeping all this in mind, right? So if we want to use traditional CPUs for encoding, right, this is economically unfeasible, right? So I mean, the sheer number of servers you would need would blow up the capex and the opex, right? So, and power and cooling is also a huge concern in data centers, right? The solution to this is video acceleration, right? So we would want to offload the entire video pipeline, right? Using an ASIC, and so that we can cater to all of these above requirements. So, AMD's MA35D is one such card, to cater to these requirements. So this is sort of focused on the data center. It uses a 5 nanometer advanced process node, right? So in order to get high channel density and low power, right? And also it is designed in such a fashion that we want to prioritize high video quality and get as close to a software encoder level video quality as possible, right? So the encoders and the decoders we support are H.264, HEVC, and AV1 standards. The video quality is comparable to the following, right? So for H.264, we can get X.264 medium preset. For H.265 or HEVC, right, we can get up to X.265 medium preset. And for AV1, we can go to X.265 slow preset. So the video quality is pretty comparable to software level, right? And now let's look at what it can do, right? It can support up to 32 1080p 60 channels, right, with 1 watt per 1080p 60 channel, and the latency is a max of 8 milliseconds for each 4K encode, right? In this chip, we also have an AI processor. I'm going to talk more about this. It has got around 22 TOPS of compute. So this is another view of what the chip has. So basically, all the video pipeline has been accelerated. So the decoder, the scalers, the encoders, right? We also have on the chip a look-ahead engine and a quality of experience engine and a compositor engine, right? And along with this, we have an AI processor or a AI inference engine. So this is like a co-processor and which is used in aiding the video encoder to improve on compression and quality. So let's switch gears and talk about the ML techniques, right, which are being considered for video transcoding. So in this pipeline, right, what we see is that people are looking at AI tools at various stages. So just as soon as we decode, right, so people are looking at pre-processing, right? So how can we change the input pixels to make it compression friendly, right? Some of the techniques would be, you could do denoising if the signal is very noisy, or if there are compression artifacts inherently present, can we remove those, right? So people are looking at those. Moving on, right? So there's also pre-analysis. So before you give the input to the encoder, right, can we look at sort of analyze the input and identify areas, right, which need better fidelity. So one of the examples is a region of interest, right? So let's say for video conferencing, that faces are important, right? So sort of ML tools can be used to detect faces, right, and sort of provide better fidelity for faces, right? And similarly, another tool is content-aware encoding, right? So knowing what the input content is, right? If the content is very easy, right, it does not have to be encoded at a very high bitrate, right? So we could reduce the bitrate. So these tools are in the pre-analysis stage, and that is our focus sort of in this talk. And as we move into the encoder, right? So now encoder is a complex beast, right? So we know that to minimize spatial redundancies, temporals, statistical, and perceptual redundancies, right? So there's a whole bunch of tools in the encoder, and most of this is hand-tuned and linear based, right? So some of these decisions can be ML driven. So we can have a huge training data set and sort of drive these instead of hand-tuned, right? We could drive it based on the data. Some of the examples can be the quantization parameter and the frame QP offset, right? We can also some of these in-loop filter parameters. So all of these could be programmed from using ML, right? And finally, at just before display, right, as a post-processing tool, right, can we use it to improve the visual quality, right? So these are some of the areas where people are looking at within the existing video pipeline, right? So yeah, our focus today, right, is on two of these tools, sort of the pre-analysis tools, where it is the first one is the region of interest coding. Basically, knowing that in few applications, right, certain regions are very important, right? So if we know this beforehand, we can use this and redistribute bits in those regions so as to improve the visual quality, right? So that is the ROI. And the content-aware encoding is knowing what the incoming input content is, right? So this will allow the content distributors to stream easy content at lower bit rates, right, without compromising on video quality, so that they can reduce streaming or CDN costs. So yeah, these are the two tools which we're going to focus, starting with ROI. So as I mentioned, right, we focused on two aspects, face and text, right? So face, we know that it's important in video conferencing, and text, in gaming and in screen sharing, right? So these are the applications which we are targeting for face-based ROI. We use ML to detect these regions. And the idea is that we provide an ROI map to the encoder where we indicate which areas the face or the text is, and the encoder then smartly redistributes the bits using the quantization parameter, the delta QP, right, based on this ROI map. So this can be, this is a visual tool, can be used to improve the visual quality, but it also could be used as a means to reduce bandwidth by operating at lower bit rates. So what was the architecture we used, right? So we took the mobile net architecture, right, and we sort of re-architected mobile net in this fashion, right? So we wanted the mobile net architecture to fit within our inference engine, right, and it has to achieve high throughput, right, while maintaining high accuracy, right? So we ended up with with designing something which has 10 times less compute than the mobile net V1 architecture, right? And then this model also can operate on HD or SD resolution, right? So that we reduce the amount of pre-processing needed. And then it will produce a block level ROI map directly, a 16 by 16 block, which can be directly used by the encoder to change the quantization parameter, right? So for text and face, right, so I've given you, we've used public data sets, trained on Coco text and for face on wider text. So we use a 5 by 5 filter. So our receptive field is 80 by 80 pixels. So we have very good accuracy for text and face, around 80 by 80 pixels, right? So as long as those faces and text are within that range, it's a very good accuracy. But as the text increases, right, so typically, the encoder itself does a good job. So we do not have to sort of detect and help it. And with respect to face, right, so only parts of these large faces are detected. Let me give you some examples of how our detection works. This is like right from our model, right? So basically, you're looking at the top two is the gaming clips, right, which has got a lot of text, and in the bottom we're looking at video conferencing clips, right? So and on the right is, you can see, as the face, the resolution of the face changes, right, we can only detect part of the face, right? So this has been productized. So I'll walk you through the inference pipeline, right? So you got the incoming input, 1080p going in. From the scaler we get RGB, right? So that goes into our ML model, which is a modified mobile net architecture, right? And then we get out a ROI map, right? And then we do some sort of some post-processing to suppress any false positive signals, right? And then this is fed as an ROI map to the encoder. So here is an example of so running using our AV1 encoder, the MA35D's AV1 encoder, right? On the left, what you see is without ROI. On the right is with ROI, and it's up, it's at 125 kbps, right? So this is 4 people. I don't know. Yeah, I don't know if you can see on the face, if you can notice a visual improvement on one or the other. So hopefully, I'm hoping that on the right is where you see an improvement. Showing some text ROI results, right? So this is a ninja clip, like a famous gaming clip on Twitch, right? So on the top is without ROI, on the bottom is with ROI using our text detection, right? And the below one is Fortnite. Again, on the left is without ROI, and the right is with ROI. Now, sort of switching gears to content-aware encoding, right? Let's set up the problem, right? So most of the transcoding today, right, we use a static ABR ladder. So it has a predetermined set of bitrate and resolutions, right, for encoding. So if you take an example on the right, what you see is that for H.264, right, typically a 1080p 60 clip would be encoded at 6 Mbps and a 720p at 4 Mbps, right? So, and when you see the gamut of these inputs, right, it sort of goes from easy, medium to hard, right? So, and spending 6 Mbps on a very easy clip, like a talking head clip, right, would be waste of bandwidth. So this is very inefficient, and sometimes, for hard clips, 6 Mbps might not be sufficient. So we may end up with suboptimal video quality. So this was the problem which Netflix sort of, for the WOD use case they've solved, right? So what they pioneered per shot encoding, right? So what they do is offline, they encode these clips multiple times. These shots are encoded multiple times in many resolutions, and then based on the convex hull, as you see, right, and for different resolutions, they choose, what is the optimum bitrate and quality, right? So this is for the WOD, right? So, but for live, we do not have the luxury of infinite latency, right? And if you want to do transcoding at scale, right, it will limit our processing capacity. So this is what we have come up with in terms of solving this problem, right? So let's define the problem, right? So how do you find the best possible quality bitrate trade-off, right, in real time with limited compute, but we need to also maintain latency, right? So what are the things we have in an arsenal, right? So we have some knowledge of the incoming content, right? So we have a limited look ahead. So with limited look ahead, we have look ahead statistics, which we can use. And then we have a deep learning toolbox, right? So we have got all this. Can we use deep learning to improve on and to optimize quality per resolution, right? So the approach is this, right? So we use the information of the incoming input, right, and we train deep neural network like a DNN to predict the optimal encoder parameter. In our case, it is the bitrate. So if we want to say if the incoming input is this, what should be the optimal bitrate that it has to be encoded with. So yeah, right. So let me sort of go a little bit more detail. So what we're looking at is right in the encoder pipeline, right. In front of the encoder, you have a look ahead, right. So a look ahead is computing all sort of statistics, right. So we have a motion estimation engine giving you block level sats and motion vectors, and you have an activity engine giving you block activity, more of spatial characteristics of the texture, things like that, right? So we want to use these as our inputs to our model. So these are the following things we use. So we use the SAD from the SAD and the motion vectors, which represents the temporal characteristics of the input, and the activity, which represents the spatial, and the Luma histogram, which is actually the input itself, right? So this is the input vector for us. Yeah, this is the input vector, and then we use a fully connected network, right? It has 11 hidden layers and one output number sort of suggesting complexity. So it's predicting what is the complexity of the given input, and we use a simple loss function, mean squared error, and the optimizer is RMS prop. Now this is the most important aspect, right? So how do we choose the ground truth, right? We believe that a minimum quality bar of VMAF of 90 is acceptable for live streaming, right? So keeping this in mind, right, what we see is that for easy clips, right, we can achieve a VMAF of 90 pretty, at lower bit rate when compared with hard clips, right? So this is the sort of the intuition behind our ground truth. For training, yeah, we have broken down our data set into 2-second intervals, right? And we have offline encoded from very low bitrate to high bitrate. Yeah, and this is how we choose the ground truth. So a little bit more details on the model, right? We have got around 10,000 segments, 70% used for training, 20 for testing, and 10 for validation. For this thing, we achieve an accuracy of 88% with a mean absolute error of around 160 kbps, right? So on the right, what you can see is a confusion matrix, the actual bitrate versus the predicted level, rounded off to a 250 kbps scenario. So what you see is that as long as we are very close to the diagonal, the accuracy is very good. And we have done more experiments, and we have augmented our data set, and we have seen that our accuracy has improved much further than this. Now that we have this model, right? So how do we use it? So let's go back to the encoder pipeline, right? So you had this encoder where you had the look-ahead in front of the encoder, right? So we use the look-ahead stats, and the complexity predictor predicts the complexity, right? And then this is going into a policy block, right? And to achieve good accuracy, we need a minimum of 4 look-ahead frames. So and then the policy block is what determines the final bitrate, which is the input to the encoder. Right? So the customers have complete control based on their use case and the requirements. So one of the sample policies we used is that we wanted to primarily preserve the quality. So the bitrate changes are very conservative. Right? So when the complexity of the clip decreases, we lower the bitrate slowly over segments. Whereas when the complexity increases, we increase the bitrate immediately so that we do not have any video quality loss. Right, some results, right? So we downloaded 100 1080p clips, which was very popular, more than 1 million viewers on twitch.tv, right? And we use our MA35D AV1 encoder, right? So and the comparison is, for the reference, we used a constant bitrate at 4 Mbps. And then we compared it against the CAE recommended bitrate, right? So we also did this experiment for different rate control modes. So for this, what we observed is that for low complexity clips, we saw that we have a bitrate savings of around 35%. And if you observe the VMAF, right, the VMAF difference is less than 1 point, right, on average. For medium clips, we achieved around 9% bitrate savings, and for high, you cannot steal bits, right? So so there is no bitrate savings there. Yeah, so this is another an assessment, right? So we use the MA35D AV1 encoder. On the left is encoded at 3.9 megabits per second with a VMAF of 94, and on the right is with CAE, right, with VMAF of 92. So, sorry, maybe if you can repeat. Sorry, I mean, yeah, I couldn't hear you. Sorry.
So when you look at live streaming like Twitch,
yes,
you often have people showing off computer screens,
right,
tutorial,
right,
and it's a very different visual characteristic than your live action.
Right.
Did you see the same kind of savings when you have both of those, or is it only when you see more live action?
Yeah, so when we see, so if you look at Twitch, right? So I mean, before a person starts streaming his games, right? I mean, a lot of time he's talking, right? And on Twitch, currently we are still for 1080p and for H.264, right? We're still sending at 6 Mbps. So there we see a humongous amount of savings, like around close to 50%, right? Yeah. So as the clip becomes more complex, like it's a gaming stats, right? And if the game is quite complex, the bitrate savings reduces. Yeah. Just a show of hands, right? I mean, do you guys find any difference in video quality from the left and the right? I mean, let me try to play this once more. Any show of hands who like left better? Okay, that's right. Anybody for right? Okay, so yeah. So yeah, I mean, yeah. So we have a bitrate savings of around 42%, and pretty close visual quality, I would say. Yeah. Yeah. Thank you. I have 5 minutes. I mean, if there are any more questions. Cool. Thanks so much. Oh yeah.
So what is the criteria, success criteria for content adaptive model to say it actually combines with visual, subjective visual assessment?
Right. So in our training, right, we ensured that we the minimum quality bar is a VMAF of 90, right?
Is that across all resolutions or 90 only
Yes,
for that?
across all of the resolutions, yes.
Okay.
Yep. And in case the input content itself is of less than 90, right? So, I mean, and typically we do not do anything in the sense, let's say if the high complexity clip coming at 85 as VMAF, right? It sort of bypasses our CAE algorithm.
Okay. And have you run this for live sports, and what is the result looking
Yes, yes. So for live sports, like for basketball, right? The savings are not much, right? But like a easy, I'm not say sports, right? Like for chess as an example, right? We've got a lot of savings there, right? For football, we've got football sort of falls in the medium, if I can sort of medium category, right? There are some savings there.
Thank you.
Thank you.